Okay, I hope everybody online can hear me again, or not again, but hear me. So yeah, yeah, I know, you missed the opening joke. Anyway, Baylor was nowhere. I'm somewhere in the middle, and in the next lecture, Ellen's going to tell you about incredibly large-scale things. I'm going to start off, I'm going to work mainly on the blackboard, but I'm going to start off showing you some pretty pictures, some motivation. And I think Keith showed you some of these at least, but possibly I'll put a different slant. Keith Julian talked about rotation and how it was important. And rotation is going to be incredibly important because it's going to break a symmetry. And that symmetry is going to lead to the coexistence of mean flows and indeed mean fields, mean magnetic fields with small scale turbulence. And that's the kind of turbulence I'm interested in. I want to emphasize Nigel's point. Nigel yesterday said, or maybe the day before, you never find the case where you have homogeneous isotropic turbulence in nature. Maybe if you get to very, very small scales, you have a triply periodic box, which you might be able to describe as homogeneous and isotropic. It's not clear that that's true, especially if you have magnetic fields. Okay, so let me just carry on. So here's the overall outline for this first lecture. So mainly I'm going to talk about my motivation. So here's my motivation. My motivation comes from various different astrophysical and some flows closer to Earth. So I'm going to talk about the sun and the solar cycle. And I know Professor Srinivasan talked about the interior of the sun. I'll talk a little bit about Jupiter, some flows on and in the Earth. If I get some time, I'll talk a little bit about some flows in fusion devices. Okay. And then I'll talk about ways you might like to model these fluid flows and talk about the difference between dynamics and statistics before I get on to deriving some of the equations on the board. Okay, I won't say what I'm going to say in the other lectures. So let's start with my first motivation. This has been my motivation going back to when I was a PhD student, but also when I was a postdoc in the here in Gila, just over the way, working with Yuri, who I'm very pleased to see is sat in the back there, on models of the interaction of convection with magnetic fields. So this is a picture. This is from Hevelius, showing sunspots. You can see the progression of sunspots as the sun rotates around. So this is mid-17th century. Actually, I usually show pictures from Galileo, which is slightly earlier, but this is such a beautiful paper that I thought I would show some of the pictures from this. So just to give you a sense of scale and how much of, Baylor really does lose, this sunspot here is about the size of the Earth. So there you go. Okay, and this is a more modern day image of sunspots. And you can see they have a very complicated structure, which I'm not going to talk about today, where you have a so-called umbra and a penumbra that surrounds it. And that's the interaction of magnetic field, which is generated, we believe, in the interior of the sun, bubbling up, coming to the surface with the convection. Okay, convection you can see at the solar surface. The sun is very turbulent, but what I'm going to argue is that you get very ordered behavior from a very turbulent flow. And that should remind you of phase transitions or condensates coming out of very turbulent flows. So let's have a look at the dynamics. So this is a movie. And what we're looking at now is a magnetogram. It's the radial component of the magnetic field. So blue is one way going into the sun, yellow is coming out of the sun. I'll play the movie a couple of times so you get an idea of what's going on. So the sun's rotating, that's the first thing. Okay. Now we're going to watch as the cycle progresses. You see the sunspots move to, why is it stopped? Oh, okay. Sunspots move towards the equator, die out, come back at mid-latitudes, move towards the equator, die out. And the cycle repeats over again. This is year, this is the year. Okay, so that was 3 solar cycles worth, roughly. Solar cycle is about 11 years. Actually, if we watch very carefully, we'll see the solar activity cycle is about 11 years, but the full solar cycle, what's happened there? It's gone. Let's try again.
You can just you can just minimize that and go back to the slides.
This is okay. I can't find my cursor now. Click anywhere. I think maybe I should just go out of there.
I think yeah. If you go to Zoom and then.
Okay. Let me just escape from that. Oh, did I just maximize Zoom? I did, didn't I? Oh no, I don't want to leave the meeting.
First you have to minimize it.
Which one's been?
The green one. And then the yellow. And now go to the slides.
Yeah. And then just.
Yeah.
Okay, we're back. So as I was saying, there's an 11-year activity cycle, but if you watch very carefully, let's have a look, focus here. We'll see we have sunspot pair of a certain polarity here. We have blue field leading yellow, blue leading yellow in the southern hemisphere, and yellow leading blue in the northern hemisphere. If you watch very carefully, as the cycle progresses, to keep your eye on one hemisphere or the other, let's keep an eye on this one. So we've got blue leading yellow, goes towards the equator, dies away. Now we have yellow leading blue, hard to see, but true. And then we go back to blue leading yellow. It's a sign of the magnetic field reversing, okay? So there's a 22-year magnetic cycle because it takes 22 years to get back to where you started, but an 11-year activity cycle. So what does this look like? Well, we've been observing it with telescopes since Galileo over here. And in the top, you can see the 11-year solar cycle. It looks a bit blurred because it's what's called the blended cycle using different definitions of sunspot numbers. And here you can see that pattern of behavior where sunspots migrate from mid-latitude to the equator, the cycle dies out and comes back again. Okay, and some of these historical observations are kind of, well, obviously the more recent ones are more accurate than the ones going back. You'll see that there's this period in the 17th century called the Maunder minimum, where the solar activity went away. And that's not through lack of observation, that's really there. There are periods where you see sunspots actually at the equator. You can see here, which we don't usually see. So here the sun's magnetic field is dipolar, and we believe here the sun's magnetic field has a quadrupole component, strong quadrupole component, and here it's mixed, right? Because we only have sunspots in the southern hemisphere, and that's an interaction between a dipole and a quadrupole. Okay. The one thing I want you to take from this is that we have a very turbulent system, but we have the solar cycle, which is large scale in space. I should have said, actually, because it was very important. When I was doing this butterfly diagram here, what I was doing is that I was averaging over longitude and plotting everything as a function of latitude and time, okay? And so we've done an average. Averaging is going to be very important in these talks. So we've averaged over longitude. We get this nice pattern as a function of latitude and time, which you can see again here. We have a very turbulent system. It's large scale in space. You can see this. It's systematic in time. I think we can safely say that. There's some degree of spatio-temporal ordering. So that's the kind of dynamics we want to try and understand, okay? Now, you've had a whole talk on this, I believe, or maybe more than one talk. The solar interior is also very turbulent, and we know how it's rotating from helioseismology. Again, Boulder's a great center for helioseismology. The only thing I really want to say here is that we have a convection zone where there's turbulent convection going on. I think Keith probably talked a lot about this. We have rotation. We have the interaction of rotation with turbulence, and that drives a mean flow, a systematic large-scale flow. And again, this one has been averaged. It's averaged in longitude again. And in fact, this has been averaged over time as well. So there's this notion of averaging. We have a mean flow where we've done lots of averaging, and we have a turbulent flow that sits on top of it. Okay. Okay, let's have a look at some other astrophysical objects. So Jupiter is a very nice planet to study. So this is an example of an early scientific proposal. Now, scientific proposals don't look like this anymore, but they used to look like this. So this is a picture. What was the success rate? I'll tell you. I don't know about the rate, but this one was successful. Successful proposal. So this was Donato Creti. He painted a picture. He painted many pictures of the astrophysics of the solar system planets and donated them to the Vatican Museum. Now you can see a nice picture of Jupiter. Jupiter is not really that big in the sky. Yeah, you can probably see that. And his idea was that if he painted these pictures and gave them to the Vatican, they may set up a telescope, an observatory, and they did. So nice idea. So one of the things that I want you to take from this picture is the one feature that you can see on this painting that you probably, if you've seen anything to do with Jupiter, you'll have seen before. The stripes. Okay, two. Sound like Monty Python. Yeah, there's stripes going across. Anything else that you might? Yeah. Oh, you know all the jokes. It's great. So there's a big red spot here. Yeah. It's upside down because he hadn't realized that when he projected it onto the screen, it flipped. So it's upside down. But that tells us something. That tells us that the great red spot, this is 1711, has been there a long time. And that's something we would want to describe using a statistical theory, I think, something that lives for, I don't know, 300 and whatever it is, 311 years. Something we would want to describe in a statistical theory, but it's not very well picked out by a zonal average. We were doing zonal averages before. This is something that's lasting a long time. It's definitely a coherent structure, but it's slightly different to the bands. I'll show you the bands. They are well picked out by doing the zonal average. So we want to think a little bit about the notions of averaging. And of course, Baylor talked about this yesterday. So we talked a little bit about the bands, the jets. So here's a NASA movie. I'll just play this through. Here's the great red spot. You see it's a vortex. You can see the motion of fluid going across. We kind of keep zooming in. These are waves. We think waves are important in maintaining the zonal flow, so-called zonal flow. Okay, so I think that one goes on a little bit longer. But if you do some averaging, say some zonal averaging of that behavior, then you can pick out the jets. Okay, so these are the jets on Jupiter, and they have certain properties. We know that the equatorial jets are the strongest and that they're super rotating. Super rotating, you have to say with respect to what frame. So they're super rotating with respect to the frame that Jupiter's magnetic field moves around in. That's what we use for Jupiter. These are the strongest ones. As you go away, you still get jets. They're kind of narrower and weaker, but they're still there. These jets are stationary. They're very stable indeed. In fact, if you take observations 20 years apart, it's very difficult to see differences in the speeds of the jets to within the thickness of a line. So they're really sitting there, very stable on a sea of turbulence. Okay, so there are two competing theories for whether these jets are driven deep within the planet or driven at the surface. And the Juno space mission, one of the tasks is to try and work out whether these are deep jets or shallow phenomena. I think it's fair to say that most people now think, okay, check who's in the audience. Most people now think that they're kind of deep, but that may not be true for the jets towards the poles. Okay. So I'll just say a quick word about the Juno because it's a spectacular mission. So, okay, so this is the pictures, the kind of pictures you get from the Juno mission. What's exciting if you do dynamo theory, which is what I do quite a lot for the generation of magnetic field, I believe the Juno mission is the closest we're ever going to get to a dynamo generated magnetic field. You might say, well, we're on the Earth. The Earth has a dynamo generated magnetic field, but between us and where it's generated, we have the mantle, which is an insulator. Here, we're very close. We're going to get very close to the action. So that's kind of interesting. Okay.
You're saying they're the analog of sunspots visible here, or that's
no? Well, we can see the poloidal, the magnetic field of Jupiter. We can see it coming out. We can measure it coming out, and it's one of the things the Juno mission is going to do, in addition to measuring the gravity coefficients, which will tell us something about the depth of the jets. Okay. So there are some jets closer to home, and there's some jets in the ocean. So I think we call them currents when they're in the ocean. But so these are jets you can get. You can possibly pick them out by eye, but they're easier to see when you do some averaging, and the averaging this time is over time, right? So you do some averaging over time. This is very different to the Jupiter jets, because the Jupiter jets, you just see them. They're there and they don't change in time. These are very turbulent. They're in a slightly different parameter regime, but they're driven, we think, in the same mathematical way, but they're in a slightly different regime of parameter space, and you can only really see the mean flows when you do sufficient averaging in time. So again, the notion of averaging is going to prove to be important. Okay. So I'll put this in, but not really because there's any jets, although there are jets in the Earth, but because this links a little bit to Nigel's talk. So this is the geodynamo. The geodynamo, we believe, I think Keith probably talked about this. We have a solid inner core. This is where we believe the dynamo. This is a fluid outer core. So this is a rapidly rotating, convecting, magnetized fluid. So we think this is a good place to generate magnetic field. Here's the mantle, here's the crust. So all the interest is going on in this region. Now, Baylor talked about balances like geostrophic balance. And I'm sure Keith talked about that too. So geostrophic balance is where the pressure force balances the Coriolis force. But of course, here we have a magnetic field as well. And so there's a lot of discussion about where the magnetic field comes into the, where it comes into the balance at leading order. I think it's fair to say that probably if you go to small enough scale, it enters the leading order balance. So the magnetic field is important. And what the magnetic field does is it breaks a constraint. So for rotating fluids, I think Keith talked about the Taylor-Proudman constraint, where the fluid wants to align with the rotation axis. If you have magnetic field there, it can break that constraint and it can make the convection more efficient. Why is that important? It tells us that if we get a finite amount of magnetic field, that can have a bootstrap effect. It can make the convection more efficient. That itself can drive better dynamo action, get more field. And what you get is a subcritical transition to dynamos. Is that a question, Nigel?
Yeah, what do you mean when it makes the convection more efficient?
Okay. So if you do a linear stability problem, and you plot the Rayleigh number at which convection sets in. Okay, this is now rapidly rotating, okay? Against some measure, let's called the Alsasser number of the magnetic field strength. So imagine we've imposed the magnetic field. Then what happens is, for rapid rotation inhibits convection. So we have a very high critical Rayleigh number. If we add some magnetic field, the critical Rayleigh number comes down. And then if you get large enough magnetic field, it inhibits the convection again. Because magnetic field on its own also inhibits convection. So what's happening here is that the magnetic field is breaking the constraint that was imposed by the rotation, and it's not strong enough to impose its own constraints. So people argue there's a sweet spot here where convection is most efficient.
Is it because the rotation acts and the magnetic field acts, or
partly, it's because, I mean, rotation inhibits convection because if you think about it, if things want to line up with the rotation axis, say we have these Taylor columns, this is not the most efficient way of getting heat from here to here. If you can break the Taylor columns somehow, you can get a more efficient mode of convection. And so you might get something where, you know, if you plot, I don't know, some measure of the magnetic field, and you have the Rayleigh number, you might have a critical onset to convection here. You might need to drive it a bit harder to get dynamo action. So you get what's called a weak field branch of dynamo action here. But then, you know, if you have a finite amount of magnetic field, you can get massively subcritical behavior. And this is very reminiscent of, and it's interesting to look at some of the methods that you've been talking about for this problem.
are you implying that the system wants to be efficient? And what variational principle?
Yeah, okay, so that's a really good, so this is a linear result.
Yeah.
You can't really say anything about the nonlinear behavior based on that. So people appeal to essentially, yeah, maximizing energy transport, say Nusselt number, for example. Yeah. So there are all sorts of things you can appeal to, but there's no rigorous theory for that. Sorry, this is a bit of a digression, but very, very interesting. And I think, for example, there are people, well, maybe I'll get to say it in the third lecture. So in the transition literature, there's an interest in trying to work out the minimal perturbations called the minimal seed, which gets you from, not from here, not going to here, but going to there. And that's the kind of thing people are doing now for the geodynamo type problem. So. So that's yeah, so that's reversals. So if you think reversals have anything to do with going through a kind of zero state and coming out again, then that would be an interesting thing to do. Okay. Wow. Okay. So I think this is my final motivation. This comes from tokamak, a tokamak device. So this is the inside of a tokamak. I'm not really going to describe fusion devices. I just want to say that most of the problems that we have in astrophysics, like driving the jets of Jupiter and things like that, there are straight analogies to do with turbulence in tokamaks. In rapidly rotating fluids, we said there's this constraint that things want to line up with the rotation axis. In tokamaks, you have a very strong magnetic field kind of going round and around the tokamak. And what that does is it promotes what we call quasi-2D turbulence, where things don't vary very much along the field lines, but vary a lot perpendicular to the field lines. So I'm going to show you a movie of some turbulence in tokamaks, if this works. So there's an instability. I'm not going to talk in any detail about this. You can see some turbulence gets generated. You can see that along the field lines, things aren't varying very much, but perpendicular to the field lines in this plane, in this cut through, there's turbulence, and you can hopefully see that there's very strong rotation. And the plasma physicists call these zonal flows. So in a tokamak, this is the zonal direction, not this. So that confused me for about a year when I first started looking at tokamaks. This is a very hard calculation to do. This is a 5-dimensional calculation. So there is no way really that this is solving for the correct physics. 5D, you know, it can't represent the range of scales it needs to. So we need some theory.
Quick question, so if there are these guiding center plasmas where it really is the Euler equation, how far away are we from that?
Quite a long way. Yeah. Or maybe I'll talk later, but this is not okay. I don't think this type of turbulence is very well described by those type of equations.
2D, you can't reduce it to a 2D slide.
They would argue not. That's why they do this. And there's a lot of discussion in the literature as to what you can and can't do.
The San Diego experimental.
But that's a difference. That's a kind of tube. That's a tube. Yeah. 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 They think the global variation in this direction is important. And so local models, they would say, don't capture the correct dynamics. And I'm not really qualified to say whether that's true or not. But if you do want to read a massive review, this is the place to read it.
What's the year on that?
2005. Okay. Yeah, sorry, I thought I'd put it there. Just to say, all of these references I will put on the Slack channel.
The zonal flow that's in here is very similar to the one that I just saw yesterday.
Absolutely. I believe it has the same, in fact, it can show predator-prey dynamics, that kind of thing, as you know. That allows you.
Only paper that put on the, like, in the stuff I dumped in, it describes this and how you divide it.
Okay, so there you go. Okay, so that's enough motivation, I think. I think we're motivated to go further. So I just wanted to talk about, obviously the theme of these 3 lectures is the interaction of mean flows with turbulence. And I think it's fair to separate these out into 2 different categories. So the first one is where you have a large scale flow that goes unstable, or maybe it's not quite linearly unstable, but a finite amplitude perturbation will trigger some turbulence. So you have a large scale flow, you've triggered some turbulence. That turbulence comes at moderate and small scales. They all interact, and then they modify the mean flow such that you reach some kind of equilibrium. So you keep extracting energy from the mean flow, you keep dissipating, the turbulence keeps dissipating things, and then you act back to modify the large scale flows, and you might think what you're doing is somehow getting yourself back to a marginal state for the mean flow. And we can all think of examples like this. So the Kelvin-Helmholtz instability, Taylor-Couette flow, pipe flow. So all of the classical flows where you're kind of putting energy in at the large scale and it's been sent down some cascade, that turbulence acts so as to modify the large scales. So I'll just show an example of this. This is actually a movie of an instability that happens in the interior of the sun in this what's called the solar tachycline. It doesn't really matter what it is, but we have a large scale flow. This is using Brad Marston's app for those of you who know about it, and if you don't know about it, ask Brad. It goes unstable to an m=1 instability. I'm looking from the pole. You can see an m=1 instability. This is a differential rotation pattern. That instability goes to turbulence. And here we are, we get turbulence, and the turbulence just rearranges the mean flow, and we settle down to some new state. So I describe this as kind of chaos from order, right? We had a very ordered flow, perhaps a unidirectional flow. It goes turbulent, so we get chaos, and then that acts back on the large scales. Okay. The second thing you could possibly do, I think, is more subtle. You put energy in at moderate scales. Somehow that interacts or with a constraint. In most of the cases I look at, that will be rotation, or it could be stratification. So you put in energy at certain scales, or it could be magnetic fields. And then because of correlations that are induced in the turbulence, that drives the mean flow. So it's the small scales that drive the large scales. Some people call this an inverse cascade, but it doesn't have to be an inverse cascade. So the large scales emerge, and this is the key, due to correlations in the turbulence, and the turbulence, sorry, and the correlations come from some underlying constraint. Okay. So I can pretty much all of the motivations that I showed you were in this category. So the convective driving of mean flows in planets and stars, we think we're getting turbulent convection, and then the zonal flow emerges. The driving of zonal flows in plasma devices, the driving of jets on giant planets, and okay, if everything I just said about flows you apply to magnetic fields, I could have inject energy into small scale magnetic fields, but because of rotation, that could build up the large scale magnetic field. That's the kind of thing that happens with the solar cycle, this large scale systematic mode. Okay, and so I have a little movie showing this one. So we're injecting energy. I'll tell you what this is a bit later on. We're injecting energy into small scales. This is a rotating planet. It goes turbulent, but there's no sign of order yet. We keep going, we keep going. What we're seeing here is the radial vorticity on a surface. It doesn't really matter what it is. But eventually the turbulence, I can use this. The turbulence arranges itself so that it's pretty much all red here. So positive vorticity, blue down here, so negative vorticity, which means it's kind of coming down here, going up there. And this is a sign of, if we did some zonal averaging, we'd get a zonal jet. So we have a large equatorial zonal jet. We have a large scale flow emerging from forcing, essentially, which is just at moderate scales. Okay. So how do we proceed? What can we do to try and describe this? Well, we could just bung everything on a computer. It's always an option. And this is the kind of thing that Baylor was talking about. So, you know, there's a huge range of scales for astrophysical objects. I mean, you know, I think I don't need to labor that point. So there's a large number of degrees of freedom. And so the non-dimensional parameters are in an extreme parameter regime. So when you're doing your computations, what you have to accept is that, and these are amazingly heroic calculations by Nick Featherston and the Boulder group, Yuri, I'm sure, was involved, where you take an anelastic convecting ball of gas, you rotate it at different speeds, and you look at the convection patterns, and you can get some incredible information about these, you know, about what the effects of rotation and convection. But what you have to realize is that this is the equivalent of Baylor's GCM. It's only really doing the large scales correctly. And yeah, so even the heroic calculations, they're equivalent of, you know, the climate models. So I'm not as optimistic as Baylor. Baylor's an optimist. So he said by 20, I forgot what you said. We'd not only be solving the full equations for the Earth, but we'd be, you know, going off to do a kinetic theory or something. So could you do that for the sun? So there's a back of the envelope calculation which says if somebody gave you the computational resources that you really wanted, you wrote a proposal and said, I'd like to simulate the sun, you could work out how much power you would need to do that. It turns out if the computational resources were available, the power required to simulate the sun is this. And so this is equivalent to the power output of a slightly cooler star. So I'm not certain 2020, I'm not certain we're going to be able to do that. So let's just see if we can think of something else to do. So I think it's important to bring mathematical models and understanding to bear on this problem. Oh, it's so important, I said it twice. Look at this. We could do reduced models, statistical models, or we could get insight from data. So I'm going to talk about all of these things, perhaps, depending on how much time I have. So, well, okay, we don't want to belabor the point. The problem is not that we don't know the equations. We know the equations. So the dynamics in the solar interior are governed by the momentum equation you've certainly seen, continuity equation, an energy equation, a gas law, and the top one is the induction equation. We'll get back into that for the magnetic field. And there's an extra force on the fluid, the Lorentz force. Okay, we know the equations. The problem is that the non-dimensional parameters are all either very big or very small, meaning the non-dimensional parameters are all ratios of time scales or ratios of length scales. So I was speaking to one of the students, I can't remember which, who said, oh gosh, these talks, there's loads of parameters floating around, which is true. And presumably you heard an awful lot about this one, the Rossby number. But there are lots of other ones. And the problem is that they're either very big, I don't know, 10 to the 20, 10 to the 13, 10 to the -7, or very small. The one you would quite like to be very small, the Rossby number, so you could do asymptotic methods like Keith presumably talked about. You'd like this to be very small, it's not, okay? It's smallish, so, still worth a go, Keith, I think, yeah. Okay, so I'm just gonna briefly go through all these modeling strategies. So I've talked about DNS. You have to realize that you're capturing a range of spatial scales. And what you're doing is you're parameterizing what's happening on the scales below, whether you know it or not. You could adopt a closure of the small scale, so we'll talk a little bit about that. These are very expensive. They're heroic calculations. They're very good at describing the dynamics of the system, but you can imagine it's very expensive to calculate statistics. If you have to run these for a long time to gather statistics, it's quite difficult to do. This is great when you can do it. So there's asymptotic theories. So Keith talked about these. So you make use of the small parameters in the problem set to get reduced equations. For example, in the Earth, the Rossby number is small, and we expand perhaps in powers of the Rossby number. Often these reduced equation sets need us to think about clever methods to solve them. So there's a lot of interesting research being done on solution of asymptotically derived reduced equation sets. This is something I'll get onto. The asymptotic approximation by a small parameter sometimes leads to what's called quasi-linear dynamics. And it's because certain nonlinearities become higher order. And we'll come back to that a bit later on. And this is an asymptotic expansion is an a priori way of deriving what's called quasi-linear dynamics. And then there's a final thing, which actually I was asked to talk about, so I'll get to that in the third lecture, I think. And so direct statistical simulation is to use our computer power to solve for the statistics of the flow instead of the dynamics. Why might this be a good thing to do? Well, the low order statistics, they're smoother in space, so they might be described by fewer degrees of freedom, and they may involve more slowly in time, or they may involve not at all, depending on what kind of averaging you're doing, and hence may be described by a fixed point or a slow manifold. The final thing, which I hesitate to put up here, is to use data. And I think you should use data when you can use data. And so you may make use of data constrained by physics to get reduced models of the complicated interactions, maybe to parameterize the effects of the small scales and constrain the dependencies in the equation sets. So if I get some time, I might talk about those too. Okay, so that's this finished. So research shows that people can't concentrate for more than 40 minutes. So that's 40 minutes. So I think we should have a break for 3 or 4 minutes. And when we come back, I'll start writing on the board. So if you want to go to the bathroom or whatever, grab a drink, do that, and we'll start again in 3 or 4 minutes.
There's a British tea thing.
Yeah, probably.
It's union rules.
Absolutely. Absolutely.
Sorry, got to take a seat.
Yeah.
So when we see the jets on Jupiter,
Yeah.
what are we actually seeing? Is this different gases?
No, it's different chemistry. Yeah, that's right. You're seeing that's right. You're seeing. Okay, I'm not an expert on this, but essentially, it's the chemistry is different because you're seeing different layers in the atmosphere.
Yeah, you see different colors in pictures. In
Yeah.
pictures, we are seeing different colors.
Yeah, absolutely.
So if assuming that they are actually different gases, why don't they just diffuse through the jets?
Oh, that is a good question. So, okay, so we might come back to that in one of the later talks. Okay, what you're seeing is, one thing you're seeing is different heights. So these are different heights. So, you know, if you spin a fluid, you can pull pull a free surface in, like a plug.
Right, like
Same is true with jets if you have a free surface. So they're sampling different heights of the atmosphere. That's the way. But also, shear flows act as barriers to transport.
shear flow.
So if you have a jet looks like this. Say. So this is a shear flow, and it makes it quite difficult to get stuff from here to here.
Do you need this board as well? Okay.
Oh, I don't need this screen.
Okay, so I can just so you'll have this board then.
Okay. Yeah. Sure. Yeah. So I'm just going to grab some water. Is there water around? Oh, there's water here. That's okay. Thank you.
The hot water is still hot. The hot water is still hot. 45 minutes.
I think we could just get the slides on the camera. So the room camera. So you won't have to join Zoom. There won't be any additional complications. The only thing is that
but I will need an adapter.
right, for the projector. Yeah, we have that. So I think the only problem there would be that if Brad has any questions, it won't appear on the room speaker. It's like if you have to say, yeah, and I'll have to say it physically. That
Is that okay? It's fine. It's fine with me. It's fine with Brad.
I think it should be fine with Brad. I'll just
Okay. Okay, so it was suggested before that because I'm British, we needed to have a tea break. So when I first got to Gilla, chair of Gilla, it wasn't Ellen at the time, it was the chair before Ellen, I think. I invited all postdocs in and said, what could we do to make Gilla better? And I said, we can have tea. This was the thing. And he said, you're British, aren't you? Yes, of course. We didn't quite think it was a good idea to have tea, but we did bring in cookies and lemonade, which I thought was a good compromise between the British tea break and Americans wanting to work all the time. Okay, so we're going to start. It'll become obvious why I'm doing this. I'm going to talk about what's called quasi-linear theory. So again, I'll put these notes online, and I probably won't do every step in the notes on the board, but they will be there for you. Right. So what are we going to do? We're going to consider the evolution of a variable Q. So Q, which depends on space and time. So, for example, Q vector, I don't know.
Sorry, I think, yeah, I think you'll have to switch off Zoom on your laptop.
Oh, okay.
Audio is coming from two places.
Okay. So I just want to quit Zoom.
Yeah, just leave the meeting.
Okay. Apologies. Okay, so I've got a vector of state variables. I could put in magnetic field here, whatever I like. Oops. Oh yeah, it's this, isn't it? Okay. And we believe that Q satisfies some evolution equation where the time variability of this Q, it varies because, well, there's a linear term acting on Q. That could be, well, it could be anything, any linear term, could include dissipation or whatever, plus some nonlinear term. And I'm going to be considering quadratic nonlinearity. So I'm going to write this as some nonlinear operator acting on Q. And we could also have, maybe some forcing. This might be stochastic forcing, this kind of thing. So just to emphasize that L is linear and N is nonlinear. These could be differential operators. And we're going to talk mainly about three different examples of equations that can all be written in this form, two of which I'm sure you've seen before. There's three examples that I'm going to take. The first one is incompressible Navier Stokes. So I'm going to write this. Oh, sorry, I've already messed up my numbering. It's equation one. We're going to be incompressible, so we'll take divergence of u to be 0. So this is equation set 2. And without loss of generality, I'm just going to set rho to be 1. I'm not even certain I'm going to use that. Can't can't be bothered writing rho all the time. Okay, I could study this equation in a rotating frame, in which case I'd have the Coriolis term in there. So I might do that, I might not. Let's see how we go. Okay, so I just want to say note, because it'll come up. In a magnetized fluid, under the MHD approximation, there's an extra body force it's called the Lorentz Force, except in France where it's called the Laplace Force. Don't ask me why we call it the Lorentz Force. Okay, J cross B, of course B is the magnetic field. J proportional to is the current. So we may or may not add in a Lorentz force term here. Certainly important in dynamo problems. The thing to note about this is that the Lorentz force now looks like 1 over mu naught curl B cross B. So that is a nonlinear term. Okay. Okay. If we're going to have magnetic fields hanging around, we better know how the magnetic field evolves. So the second equation I'm going to consider is called the induction equation. And then the framework of MHD 2. What happened to 3? Okay, that's good. This is equation 3. Apparently. And this has an evolution equation. Looks like this. Of course, we know that the divergence of B is equal to 0 as well. If the divergence of B is 0 and the divergence of U is also 0, so we're considering an incompressible fluid, which we are, then you can write this equation in the same form as the vorticity equation. So I've put in a few exercises. You can do that for yourself. It's just you just do this by expanding the curl. And this is derived by combining the pre-Maxwell equations. So we're going to get rid of the displacement currents. With Ohm's law for a moving conductor. The simplest Ohm's law you can get through an MHD. This is J. Okay, and I've left it as an exercise for you to derive the induction equation from essentially Faraday's law in this. Oh, well, okay, so we have a card carrying astronomers here. So yeah, okay. What, with all sorts of 4 pi squares floating around and things like that? Who knows? Okay, we do this just to confuse you. Okay, the third equation, which I've derived in the notes for you, but it'll probably take too long to derive on the board. And I think you've seen it before. It's sometimes called the barotropic vorticity equation. Okay, so again, as I said, I've derived it for you here. And this takes the form, I'm going to, so I have a velocity, u, v, w, I'm going to take the vertical component of the vorticity, which I'm going to call zeta. So zeta is that component of the vorticity. So it looks like dxv minus dyu. I'm going to consider two-dimensional flows for reasons that I'm not going to tell you. So I'm going to think about V and, well, I am going to tell you, but they're only in the notes, looking like functions of X and Y. And so what I can do is write U and V in terms of a stream function. I'm sure you've seen this before. And zeta, the vertical component of vorticity, turns into the horizontal Laplacian acting on psi. Okay, so again, this is all done for you in the notes. And we can derive an equation, an evolution equation for zeta, the zeta of t plus the Jacobian of psi and f, and this is going to be the planetary rotation. Plus zeta equals, well, dissipation and forcing. Whatever those are going to be. So you can see I've got a term, it's of the correct form. I've got a term which is the evolution of my variable in all cases. Here I've got a nonlinear term because psi is related to zeta by this. So this is a nonlinear term. I've got a linear term here. And the dissipation and the forcing are either, well, forcing, and this is usually considered to be a linear term, okay? This one's quite interesting because formally, this equation here, the induction equation, is formally linear in B. For a given U, it's linear in B, which means when we do some of the tricks, we can get a bit further with this equation than we can with this equation. This equation is inherently nonlinear. There's nothing you can do. This equation is linear if you consider U to be given and just solve for B. It only becomes nonlinear in B when you get the Lorentz force, and the Lorentz force goes back and acts back on the velocity. And actually, you can make use of that fact when you're deriving the set of equations, which we will do. Okay, does anybody have, this amazingly is equation 7, which tells you how much work there was between there and there. Okay, has anybody got any questions about those equations? Yeah. Sorry, say that again. Oh, sorry, J. Yes, thank you. J is the Jacobian. So J of F and G is, sorry, F X G Y minus F Y. Yeah, so it's a nonlinear. Yeah, thank you. Thank you. Yeah.
So for Barotropic, you just have the equation for W for vertical velocity.
No, okay. So in the notes, I'll explain why you don't need the equation for W. Essentially, wow, there's lots of ways you can think about it, but if you just have hydrostatic balance in that direction, you never need to find W. Sorry?
It doesn't convert.
Right.
So, yes, you don't need it.
You don't need it.
Yeah,
Well,
it just swirls around in it.
okay. So those are 3 types of equation that all look a bit like this, and we'll certainly look at these 2. I think. Let's think. Okay, so what are quasi-linear theories? So I'm going to keep writing QL. So I just want to give a bit of a historical perspective. I should say most of what I'm going to say in the next 3 lectures is in a review that I wrote with Brad. It's going to come out in annual reviews of fluid mechanics, but it's currently in the archive, and that's one of the papers that I put on the channel. Okay, so I think it's fair to say that certainly in fluid dynamics, the early ideas come from Malthus in 1954, who looked at convection under some quasi-linear approximation. And then there were papers coming after that by Ledoux et al. And Ed Spiegel, and I think a seminal paper, again with a Boulder connection, is by Herring in 1963. Say a little bit more about that. So these are from the fluids community. Of course, whatever you do in fluids, the plasma physicists always say they got there first. It's kind of one of the annoying things about plasma physics. But it's not true in this case, although they say it. So the first paper we could find, we did an extensive search by the plasma physicist, was in 1960. This is a paper which has some very eminent authors on it in the et al. So it has Jackson. So if you ever studied electrodynamics, classical electromagnetism, you probably use Jackson's book, and it has Gelman as well. The first paper, which I think uses the word quasi-linear though, is this paper by Viedinov et al. In 1961. And then there's another paper. So this one's quite difficult to. Okay, so these are plasmas. So this is a good case where actually the fluid dynamicists got there first. And one of the things we're going to be looking at is explaining these things using diagrammatic representations, kind of Feynman type diagrams. And they certainly appear in Viedinov et al. And an early paper, which I'm sure is familiar to many, is the one by Hasselman, 1966. He was considering wave-wave interactions. In a kind of diagrammatic way. So coming back to Herring, Herring has this statement in his paper, which I'm not going to write out. He says, the discarding of the fluctuating self-interaction then corresponds to closing the system, we'll see what this means, of moment equations by discarding the third order cumulants. So in the third lecture, I'm going to talk about doing what are called cumulant expansions. And I think Herring is the first person who talks about the quasi-linear approximation as being equivalent to discarding the third cumulant in an expansion. Okay, so I've spent a lot of time talking about turbulence and mean profiles, mean properties. So this ensures we need the idea of an average. Okay, so I'm going to spend a little time talking about averaging choices. And Baylor did cover some of this yesterday, but no harm in doing it again. So what you'd like to do, I mean, if you can't solve this, I mean, why are we doing this? Let's go back. We've got this set of equations here, okay? If we could solve this set of equations for Q, we just solve them, right? But we can't. But what we might want to do is solve, for example, for the average properties of Q. That might be a thing we want to do. And so what we have to do is define the notion of an average, and then try and derive equations for the average of whatever it is we're doing, plus the thing that isn't the average, which we're going to call a fluctuation, okay? So we're going to derive and solve for the average properties of the state variables. So I'm going to write Q, my state variable is, well, quite easily some average plus a perturbation. Perturbation is just defined as, you know, this minus this. But I have to decide, what do I mean by averaging? We would quite like, although it's not necessary, we would quite like the overbar to be a linear averaging procedure that satisfies what are called Reynolds rules. And this is sometimes called the Reynolds decomposition. Going back to Nigel's talk. So the Reynolds averaging rules are, well, there are a few of them. So if I take two Q1 and Q2, an average, then I would hope to get Q1 average plus Q2 average. If I take Q and I average it, and then I average it again, I'd quite like to get just Q averaged. This makes kind of algebra easier if it satisfies these. This is the one that's hardest to satisfy. Put it over here. If I take Q bar and multiply by Q and then average that, then it would be nice, though actually not necessary. And I think Baylor showed some examples where this is not true, that this is true. Okay, so we'd quite like this to be true. Okay. Over here. Okay, so what are the possibilities? And we've kind of talked about most of these, so I won't labor the point too much. Could do a spatial average. So what am I doing here? Well, I'm going to assume fluctuations, so the prime variables are on a scale L0. L0 is very much smaller than some system size. And I just define an intermediate scale I'll call it A. So intermediate just means somewhere in between the two. And then I could write Q bar is it's exactly what you think you might do. You integrate over a small ball in space. To get the average, and the small ball is at the intermediate scale. So V is a sphere particularly a sphere of radius A. So that's kind of obvious. One other bit of averaging in space that we've seen is when we looked at the solar cycle, we saw that we just averaged over one component, right? Over one direction, right? So we did a longitudinal average. That's also a sensible thing to do. Though of course different. I was struck at how quickly Nigel could erase a board. It's amazing how fast he can do it, right? You must, I was thinking you must train how to do it. Is that you have competitions, do you? I see. There you go. Okay, so we could average over one. Over a coordinate. So you've all seen this kind of thing. So if I had Q, for example, which is a function of R, theta, and phi, then I might write Q bar, R theta, I don't know, 1 over 2 pi times the integral from 0 to 2 pi. This. This is sometimes called coordinate averaging. We're going to do quite a lot of this, usually in this direction, usually averaging over the zonal direction. We could do temporal averaging. So you remember me saying, actually, this possibly is not a good one to pick out the great red spot of Jupiter, but this one might be because it's been there for a long time. This one could pick out the jets. Temporal averaging is essentially you do a very similar thing to this. So you have to construct timescales. So if Q varies on a, sorry, if Q prime, oh, sorry, no, Q varies on both a rapid timescale and a slow timescale. We'll call the rapid timescale T0 and the long timescale T. Then you can average over an intermediate timescale tau. I'm going to define tau to be somewhere in between the two. And move over here. So I might define Q bar. This is oops. Okay, so again, I've got some fast varying thing, I've got some slow varying thing. If I pick an intermediate timescale, the fast varying thing is going to integrate to 0, and I'll just be left with the slowly varying thing. And finally, we're going to think a little bit, and again, Taylor talked about this, about ensemble averaging. So if there's no separation of scales, so all of this is relied on things being fast and slow or small and big, but if there's no separation of scales, you take an average, you can take an average over realizations. So I start off with lots of different initial conditions, for example, of my PDE, say that one, which has gone off the board, and average over the realizations. And of course, this has already been mentioned. If the system is ergodic, well, who cares? It doesn't really matter. However, for things that we're going to look at, it's very rare that the system is ergodic. Think about Jupiter, right? You've got this great red spot there. It's quite clear that, you know, these averages are not going to give me the same answer. And finally, probably a good place to finish, largely because I'm knackered, is we could do averaging by filtering, and this is Baylor talked about. So hopefully this should give you all a warm feeling, because I'm sure you're all happy with these concepts. So, you know, we could do spectral filtering. So perhaps we take our, you could do spectral filtering in space or time, but I'm thinking really in terms of space. So you take your signal in space, you do an FFT of it, you maybe keep a few modes, throw away all the others. So we'll come back to that a bit later on. There are other ways of filtering. This is, you can think of this as filtering in Fourier space. You can filter in real space by doing Gaussian filtering. And there's a very beautiful paper by Germano, 1992, which talks about Gaussian filtering. Now, these don't necessarily satisfy the Reynolds rules.
So what's special about this paper? I mean, Gaussian filtering is in some sense trivial.
It is in some sense trivial, but okay, so Germano talks a lot about the Reynolds rules and whether they satisfy and what you should be doing. You know, have a look at the paper. It's a very nicely written paper. Yeah, it's not. I mean, as you say, Gaussian filtering is trivial, but then when you get some nonlinear terms, you take the product of filtered things. What should you be doing? That's kind of it.
What I think is important about the Germano paper is he introduces the idea of a test filter.
Yeah.
So you use a grid scale as a filter, but you also filter deliberately at a larger scale. You compare the two, and then if things are supposed to be self-similar between those scales, you can take advantage of that.
Yeah. So just to finish by saying these don't necessarily, well, they don't satisfy the Reynolds rules. And if you want to go away and think about spectral filtering, have a think about this one. Go away and have a think about this one and see if you think it's true for spectral filtering. But in some cases, if you throw away some interactions, they can be made to, okay? So I think I'll do ... and we'll leave it there. And what I'm going to go on to next time is to talk about the quasi-linear approximation, which is what we're going to do is we're going to derive an equation for the mean, an equation for the fluctuation, and we're going to do some damage to the equation for the fluctuations. And that's going to be called the quasi-linear approximation. Okay, definitely time for tea. So thanks for your attention.
Any time for questions?
I haven't said anything really at the moment. So, Yeah.
Is there some intuition for when an averaging process should or shouldn't obey the Reynolds?
Most of the ones you think of do, right? I mean, pretty much, if you take something that's, a kind of linear, yeah, something like a spatial average or a temporal average, I mean, it just naturally does, because you're kind of doing linear operations, essentially. The reason that this one doesn't, I really encourage you to go away, sorry, this one, the spectral one doesn't, is to think about what happens when you multiply things together. I think that's the thing to think about. And so when you multiply things together in real space, that's not the same as multiplying, that's really a convolution in spectral space. And so things don't quite work out the way you might like. But the thing to do is just take some functions, filter them, and then try and see where you go wrong when you satisfy this, when you try and satisfy this one.
Say more about this ensemble averaging and why this separation.
Well, okay, it's not, you can do it when there is separation of scales. Okay, it's not that you shouldn't do it when there is separation of scales. All I'm saying is this relies on there being a separation of scales. So if there isn't a separation of scales, I can't do this. Okay. This one, again, relies on me having a separation of scales. If there isn't, I can't do it. So eventually, if there isn't a separation of scales, I'm running out of things to do. So I'll try ensemble averaging. It may be that ensemble averaging is the best thing to do, even if you do have a separation of scales. And we'll come back to that. But certainly, if you don't have a separation of scales, you're kind of running out of things that work. So,
I mean, it's randomly driving or something, and there's a natural.
Right. If you have a chaotic dynamical system as well, you think about it, you start off with lots of different initial conditions, they all go off. You could average over the, yeah.
Does that mean you have to run the or collect data many times so that you have
Well, you may, or you could derive equations for what you think the PDF should look like, for example. And that's what we're going to do. Sorry? If you have a PDF, that's right. So if you know the equations, you can derive an equation which the PDF should satisfy. I'm not saying you can solve it, you can certainly derive an equation. Then you might say, what is the mean? What is the fluctuation about the mean? That kind of thing.
All right, let's have some people do that. Really cute dog.
It is.
I have a border collie.
Okay, so he's a bit younger there, but he's quite old now.